Earth Science Introduction to Volcanoes. What a great picture you're looking at. Here we see a volcano right behind this city, Tacoma, Washington. If you're living next to that volcano, what 3 questions would you want to know? It is a volcano that will blow up someday. So what would you like to know before you bought property next to that beast? For example, how often has it erupted over history? When did it last erupt? Where did the lava flows, lahars, and pyroclastic flows occur in the past? In other words, you may not want to buy property in the middle of where a lahar or a pyroclastic flow came down that mountain at a high rate of speed. You may not want to own that property. What kind of earthquakes are occurring now? Because you will experience earthquakes next to a live volcano. There's 1,500 active volcanoes worldwide. A third of those have records of previous eruptions. In other words, they've erupted in the time span of when humans can remember. 500 million people live near active volcanoes, and so it's real common to have volcanoes in the vicinity where somebody lives. Here's some pictures of mud flows, volcanic mud flows from the Nevada del Rios volcano in Colombia, and it killed 23,000 people. Mud flows came right down the valleys and just swallowed up villages. VDAP scientists, or the Volcano Disaster Assistance Program, traveled to the Congo to examine an eruption of the Nyiragongo volcano in 2002. One of the problems of the volcano there is that toxic gases, i.e. like carbon dioxide, which is heavier than air, can flow out of the volcano. And if it does, it can go down the slopes and asphyxiate anything in its path. Fortunately, the toxic gases were trapped in Lake Kivu and didn't do as much damage as they could have. Lava from the volcano was several meters thick. There's a picture, and it burned and destroyed buildings in Goma. In Cameroon, volcanic gases from Lake Nyos killed 1,700 people in surrounding villages. And there you see some dead animals, and thankfully not pictures of dead people. But there's an example when carbon dioxide came down and killed people next to the volcano. Here's if this doesn't play, right click it and click play. But here's an introduction to volcanoes and hotspots. We talked about hotspots when we talked about Hawaii, and we were talking about plate tectonics. But here we have a mantle plume with a hotspot coming up. The plate moves, the hotspot stays in one spot. Volcanoes erupt. The plate continues to move, and then once the volcanoes quit building, they go ahead and shrink from erosion. You see the little sides on the volcano because those would be coral reefs that would grow, coral atolls. And here we see an example of hotspots in the Pacific Ocean with guyotes up there in the northwest of it. And it's going to play again. I'm going to go ahead and go to the next slide. There's a trail of underwater mountains that you see in the picture as that hot spot has erupted and then formed a mountain, and then the plate has moved, and you can tell where the plate has moved, and the plate has changed direction in the past. Crustal movement was that direction. Crustal movement was that direction. May 18th, 1980, Mount St. Helens erupted, and the cascade mountain range on the western side of the United States. And it's interesting, I clearly remember this eruption because I was married a month and a half later, and I have relatives that live in Washington, and they brought Mount St. Helens souvenirs from Washington to Kansas, where I was married. One of those was a pitcher that somebody had fired and used the ash from the volcano to put a brown glaze on a clay pitcher. Another one was a pencil that I still have that has ash inside the pencil. You can see little gray ash, but the ash came all the way across the United States. Here's an example of the Cascade Mountains with the subduction zone that we studied in the chapter on plate tectonics, and we'll continue to use these kind of slides as models throughout the earth science course. So you want to really have a good handle on plate tectonics. What type of magma is associated with Mount St. Helens? Well, typical for volcanoes popping up above subduction zones, it's andesitic. And we'll look at the type of rocks in the next chapter. Mount St. Helens eruption in 1980. Here's a picture just before it erupted in March. Remember, it erupted in the middle of May 18th, 1980. So unrest was featured in early March. Not really newsworthy, but it had minor earthquakes, minor eruptions, earthquakes, release of volcanic gas. Volcanologists started paying attention though. And it was followed by a change in the shape of the cone. Notice the bulge up in the north flank of the volcano, and an increasing frequency of earthquakes. Here's an example from top down to bottom of the May 18th eruption. A moderate earthquake triggered a massive landslide on the north side of the volcano. And so you can see in B the debris avalanche is coming down the volcano. That debris clogged streams, and the pressure was released on near surface magma, and there was a lateral blast that erupted toward the north, and then a later vertical eruption. So it wasn't a pretty eruption, but it was certainly devastating. It just took out one whole side of the mountain. So if we measure Mount St. Helens eruption, and here's a good picture of it compared to other eruptions, there's 8 divisions on a logarithmic scale that increase times 10 between divisions. Remember, the logarithmic scale is by a scale of 10, and Mount St. Helens was on a 5. Some more about measuring the eruptions. There were later eruptions that occurred with Mount St. Helens, but they were much smaller. The big eruption was a VEI rank of 5. VEI stands for Volcanic Explosivity Index. A lot of the loss of life of the volcano has to do with mud flows or tsunamis, as opposed to the actual lava or pyroclastic flow right next to the volcano. Here's a picture of a volcanic eruption. Shows the different types of products that come from an eruption. Prevailing wind in this picture is from the left, and so you have tephra and gases coming up immediately from the volcano where it erupts. You have a lava flow right next to the eruption. Magma is what we call liquid rock when it's underground, but once it erupts onto the surface, we call it lava. So it's important to know the difference. Magma and lava. Magma is underground, lava is on the surface of the ground. You get landslides on the volcano. You get a big eruption cloud. The sky fills with dust, and planes can't fly through that because it'll eat the jet engines up. And then from the dust in the air, you'll get acid rain. So there's the good news about volcanoes is after the volcanic dust settles down and starts to weather, it's got lots of minerals in it, and it's very good for plants, but not immediately. Continuing with Mount St. Helens, Mount St. Helens explosion reduced the height of the volcano 400 meters, and so you see a before and after picture. Change in elevation was 400 meters, and you see a picture of a geologist, Greg Johnson there. He died on site, and Johnson's Ridge is located 10 kilometers from the volcano, so you don't want to be very close when a volcano blows up. Here we have a picture of a map of the explosion. Mount St. Helens is in the kind of the center right there, and the red is pyroclastic flow. Now pyroclastic flow is a volcanic debris kind of flow that comes out of the middle of the volcano, very fast, hot rocks. And then you have a debris avalanche that came right down the stream, and then lateral blast deposits would just be stuff that's blasted out of the volcano and just wipes everything out around it. And then you see mud flow deposits that come right down the rivers, and they can move really fast as they follow the stream beds out of the center part of the volcano. The reason we're using Mount St. Helens is just as an example of what happens when a volcano blows up. We're talking about products of volcanic eruptions. One of those is tephra. The definition of tephra is it's particles that are blasted into the air by the eruption. The pictures on the left are volcanic bombs. They're blobs of magma that's solidified and then crashes down. So magma gets thrown into the air and then crashes down somewhere. And volcanic ash can get transported way downwind. We even, with Mount St. Helens, we even experienced seeing some of that, just very minor amount of the wind-blown ash clear into the Midwest. So here's Mount St. Helens blowing, and now when Yellowstone blew, it went a lot further. You can see ash beds all the way down into Louisiana from Yellowstone. Yellowstone is at VEI index of 8, so it's much larger than Mount St. Helens. Okay, so airborne eruption products also include volcanic gases, which is water vapor, sulfur dioxide, and carbon dioxide. And those volcanic gases can affect climate patterns. What sulfur dioxide does is it blocks insolation temporarily, like up to a year, and temperatures get colder for that year. Carbon dioxide can create higher temperatures, and that we think happened with lots of volcanic activity taking place 120 to 80 million years ago during the when the dinosaurs ruled the earth. One of the things that's interesting, if you look at the history of English weather, when Krakatoa blew in Indonesia, the next year the British had the coldest weather they'd had for a long time, and we believe that's because the Krakatoa eruption in Indonesia cooled the atmosphere enough to make the weather in England cold that next year. Okay, so eruption products on land. Here we see lava flow. Lava flow with low viscosity can flow up to 50 kilometers from its source. In other words, it's just a river of hot rock. Lava can flow in tubes. In other words, what happens is the outside of the lava cools, and then it flows in the middle of the tube. And so then those tubes can build up in layers, and you can actually see those layers. The low viscosity lava can flow 50 kilometers, and here's an example of what can happen. We got a nice restaurant there on the top picture, and as the lava flows over that restaurant, it solidifies and builds up, and there's some guys standing next to that sign 10, 12 feet in the air. So that lava is 12 feet higher, just covered over everything. The highest viscosity lava remains close to the volcanic center because it doesn't flow well, and the lava that was at Mount St. Helens would have been a high viscosity lava. It wouldn't have gone very far. Now pyroclastic flow is highly dangerous. It's fast moving. It can be up to 700 degrees centigrade, and it's a dense cloud of a combination of volcanic glass and tephra. So that ash and volcanic glass can just spill right down the side of the mountain. And there you see a picture of what happened with the pyroclastic flow in the lower right. Man looking at what used to be a city. Lahars are mud flows that form when a volcanic debris mixes with streams or melting ice. And a lahar commonly is along a stream channel, and there you can see a lahar that had flowed from about the top center of the picture, and you can see the marks on the trees where the flow was, and then it went on downstream. So it was 20 meters deep around Mount St. Helens. This is a picture from Mount St. Helens area. Let's go ahead and order the products that erupted from Mount St. Helens in order of which traveled closest to furthest. This is not in the right order, so let's put them in the right order. Well, we said that lava in Mount St. Helens was a high viscosity, so it wouldn't have traveled very far at all. And pyroclastic flow is tephra mixed with gas, and it would have been immediately around the volcano. And then ash would go a long ways because it would get in the air and just move. And then lahar would be follow the stream beds around the volcano. So let's see what kind of order they are. Well, there we are. Lava, pyroclastic flow, lahar, and ash. Ash would go the furthest in that particular type of volcano. Now, if you have a volcano with a low viscosity, in other words, real runny lava, the order might be different. And we see a real runny kind of lava in the mid-ocean ridge area, or in the kind of lava you get in the hot spot like at Hawaii. It's a real runny, whereas the lava coming out of a andesitic lava from like Mount St. Helens is real sticky and doesn't travel far. By the way, if you notice in the picture, you can see some people standing on the edge of the crater, just on the very edges of the top. So it kind of gives you a scale of how big that is. Okay, here we have a Venn diagram comparing Mount St. Helens to Nyiragongo. Mount St. Helens is located near a convergent plate boundary, and Nyiragongo is near a divergent plate boundary. Nyiragongo's produced significant lava flows. Mount St. Helens did not. And Mount St. Helens erupted after a century of inactivity. Nyiragongo continues to erupt. So several eruptions over the last century. Both had a few monitoring instruments prior to the unrest. Now they have more, but before they started blowing up, they didn't have any. And that's a new field anyway. And both had volcanic gases released prior to the main eruption. Both had frequent earthquakes associated with the unrest. Both had unrest that lasted for approximately 2 months before the eruption. So if you start seeing unrest in a volcano a couple months, you may not want to be close to the volcano. Both had an eruption that occurred during daylight. Nyagongo is located within 20 kilometers of a large city. Mount St. Helens is out in the middle of the forest. Volcanic activity subsided after about a week for both. Nyagongo is a low viscosity magma, so that means it travels a long ways, so the lava is dangerous for a long direction. U.S. Geological Service geologists did aided in interpreting both types of volcanoes. Death toll was less than 100 in Mount St. Helens and more than 100 for Nyagongo. Both had the shape of the volcano change, and Mount St. Helens had a massive lateral blast. In other words, it blasted sideways. One thing that's really important, even as a tourist, is to recognize different types of volcanoes. And one of the reasons I like earth science is just because everywhere you go, you're going to see earth science. So it's one of those fields that you're always going to apply. So if you go to Hawaii, you're going to find a shield volcano. If you go to Japan and look at Fujiyama, you're going to see a stratovolcano. If you go to New Mexico and go to northeast New Mexico, you're going to see a cinder cone. Different types of volcanoes, different types of slopes, different types of lava. Shield volcanoes. Well, they have broad, gentle slopes. They have low viscosity lava, and they come out. In other words, it's a basaltic lava. Is the kind of lava you get that's low viscosity. And the eruptions are real mild. You can stand next to the eruption and you're not going to get hurt. It's going to be hot, but you're not going to get blown. It's just the lava just kind of dribbles out of the ground. Stratovolcano combines a cinder cone and a shield kind of volcano. It's kind of in the middle, and that's what gives it this nice, beautiful, rounded slope, concave slope on both sides of the crater. It's the most common, and the one. It's got steep slopes built from alternate layers of tephra and medium viscosity or andesite lava. And it forms on plates overriding subduction zones. So these are the kind of volcanoes you find all along the Cascade Range and in Japan and along the Andes. Beautiful, beautiful volcanoes. And so the combination of the two different types of lava create that nice shape that we see. Cinder cones are just a pile of volcanic cinders that blew out of a hole in the ground, basically. And you can walk around that. I've walked around the one in northeast New Mexico. It's fun to go to. And it just sticks up above the ground 400 meters or so, and slopes are not too hard to get up. You can find cinder cones in the middle of the Rift Valley too, and you can actually walk up on top of the cinder cones in Kenya. Here's a question: what type of volcano was Mount St. Helens? Well, it is a stratovolcano. In other words, it's that middle. Now that thing's blown up enough; it doesn't have that nice curve because it keeps blowing up. Okay, another volcanic landform we can see is a caldera. And a caldera is a collapse of a previous volcano. And there you see a volcano that's giving off some gas in the foreground. Yellowstone, Wyoming is a huge volcano. Another volcanic landform is a lava plateau, and you see that in the Columbia Plateau in Washington and Oregon. Great big wide lava flow, real thick 10 to 20 meter thick basalt, and the whole southeast side of Washington State is covered by that basalt. There's some different lava plateaus around the world. I remember seeing a huge lava plateau driving across Ethiopia when I was a kid. And Ethiopia is full of volcanic features. It's really interesting. And also, when I lived in Bangalore as a kid, the Deccan Plateau is a real old volcanic lava plateau. And you can just see miles and miles of basalt along that plateau. The other thing you might find with volcanoes are geysers, hot springs, fumaroles, mud volcanoes. The definition is there. A geyser is a water heated under pressure with volcanic gas and blows up on a regular period of time. Old Faithful in Yellowstone is an example. A hot spring is a heated underwater that rises to the surface. A mud volcano is a chemical reaction that converts rock to clay and spurts up mud. And a fumarole is a volcanic gas that escapes when you don't have water around. So water makes things tend to blow. So a fumarole doesn't have that pressure behind the steam of the water. In the talk where we introduced volcanoes, different types of volcanoes, we talked about magma, and in this lecture, in our earth science class, we're going to talk about specifically about different types of magma. Well, escaping gases from volcanoes drive the volcanic eruptions in them. And how easily gases escape from magma is controlled by magma viscosity. Viscosity is how sticky that magma is. If you're making cookie dough, it would have a high viscosity, whereas a milkshake would have a low viscosity, or a milk would have a low viscosity, even lower viscosity. We said before, and we'll say it again here, you need to know the difference between magma and lava. Magma is molten rock below the surface, whereas lava is molten rock on the surface of the earth, or another planet for that matter. Viscosity by definition is resistance to flow. So viscosity depends on temperature and magma composition. Depending on the mineral composition, the type of minerals or elements in that magma will depend on what type of viscosity it has, and that composition depends on the plate tectonic setting. You get andesite type of rocks near subduction zones, and you get basaltic type of rocks near mid-Atlantic ridges or mid-ocean ridges. The reason you get andesitic type basalts near subduction zones is because remember we had partial melting, and so the composition of the basalt partially melts. It removes some of the heavier minerals out of it, and it becomes lighter. And so if you had to float, andesite would float on top of basalt because it's lower specific gravity. And remember that favorite verse of mine, God has created a boundary that the oceans will never cross in Psalm 104. So we have 4 materials here: maple syrup, milk, peanut butter, frozen yogurt. Let's put those in the correct positions, A, B, C, D for the relative viscosity. So milk, maple syrup has a higher viscosity than milk, peanut butter is higher viscosity than maple syrup, and frozen yogurt more than peanut butter, mainly because it's frozen. If it was not frozen yogurt, we might switch it, and peanut butter would be the highest. So here's some examples of viscosity, and increase of viscosity is to the right. So air has a really low viscosity, then water, then canola oil, then motor oil, then corn syrup. And basalt lava has the liquid lava has about the same viscosity as corn syrup and peanut butter. Then you have andesite lava, which is more like tar, and then rhyolite lava is stickier than tar, like a heavy tar. And then mantle rock is very high viscosity. we said that escaping gases drive eruptions. As gases are dissolved in the magma. The magma that turns into rock has lots of gas in it, lots of water vapor. And depending on how much gas is in it will affect that viscosity of the lava. The more gas, the more viscous it is. By the way, when talking viscosity, that's important with motor oil. You know, when you I don't know whether you change the oil in your own car, but 10W30 has a number 10 versus a number 30, and those W stands for winter, so the viscosity of that oil is 10 in the winter and 30 in the summer. Okay, so even driving cars, you need to know what viscosity is. Let's see. A carbonated drink is a good example of gases that are released as pressure decreases. You open a 2-liter pop bottle, and it will fizz because the gases are the soda is starting to degas, and lava works the same way. You take pressure off and it starts to degas. All the other factors being equal, which magma would flow the fastest? Well, a low viscosity magma flows faster because it's not as sticky. Like milk would flow faster than peanut butter. Just think about that. Well, how would the viscosity of motor oil in your car's engine change from the time you turn the key in the ignition to when you've driven 50 kilometers? Well, it gets hotter, and when something is hotter, it makes things more viscous or less viscous. In other words, it flows better. And so if it gets too viscous, then it doesn't lubricate the engine as much as it wants. So the engineers that have made your engine have worked really hard to give an oil that can start your car, but then also still lubricate. Now, if you lived up in Canada or in North Dakota or somewhere, you might have to get a heater for your oil because it gets so cold that the oil turns to sludge, and then the car won't turn over. So you have to heat your engine up at night or when you park your car to keep the viscosity low enough that, low enough that the car will actually use the oil. So viscosity depends upon magma composition, and mostly that's how much silica, or the silica is the combination of the element silicon and the element oxygen. And if you have very little silica, you get a low viscosity. If you have lots of silica, you get a high viscosity. Low viscosity, less silica; high viscosity, more silica. Well, basalt is a dark color. Dark rocks like basalt don't have as much silica in them, and they're low viscosity. So it all starts to fit together. Rhyolites are a lighter color rock, and they have lots more silica in them. Lighter color rocks tend to have more silica in them, and so they're a high viscosity. In other words, they're sticky. Here's a diagram of the different types of rocks, and we'll look at rocks, different types of rocks, and some pictures here in the next chapter. But basalt has a silica content that's less than 53%, whereas rhyolite has a silica content of more than 68%. And notice that basalt is a much higher temperature magma, whereas rhyolite is a lower temperature magma, and andesite's in the middle. By the way, andesite is, remember, what we find over subduction zones. Basalt is what we find over the where the oceanic ridges. Okay, which type of magma is most likely has the lowest viscosity? And here's a little diagram. Well, low silica content, high temperature. has the lowest viscosity. So remember, when you start your car and run it for a while, the engine gets hot, and that lowers the viscosity of the oil. Well, the same thing's true with rocks too. Then if you have low silica, in other words, not much silica, is just like sand. Think of sand in your sandbox, or quartz watches. The quartz in your watch is silica. If you don't have much of that, then it's going to be real runny. There you go. Well, I won't try and do a stupid poem. Okay. More viscosity has more violent eruptions. In other words, what happens, you get sticky lava, and the gas pressure builds up behind it, and finally it explodes. And that's why it's a lot safer to be next to the low viscosity lava coming out of the shield volcanoes in Hawaii, because they don't have that explosive gas behind the lava. So here we have a violent eruption. Again, that's Mount St. Helens. So let's take this viscosity concept to milk in a milkshake. You put a straw in your milkshake or in your glass of milk, and you blow bubbles through it. Well, which one's going to splat up in your face? Well, the milkshake's going to, because it has a higher viscosity. Milk has a lower viscosity, and so it's not going to splat in your face when you blow a bubble out of it. How would you classify the viscosity of magma that produced the eruption of Nyangongo and the violence of the eruption? Well, there's a low viscosity and a mild eruption. Just kind of ran down the slope. And that's because it's actually part of a rift system there. It's not over the ocean, but it's part of that African rift system where these plates are starting to spread apart, and it's a same type of volcano you got there that you have in Hawaii. Viscosity depends upon magma composition or silica content. We've talked about this. Why does silica vary? Well, it varies because the source of the magma is different. Remember, in plate tectonics, over a ridge, the source of the magma comes from the mantle rising up from convection current, and over the subduction zone, you have the source of the magma from partial melting of ocean ridges, and the lighter materials from the magma rise up as liquid lava. So it's differentiated so the heavier stuff does not rise up into the volcano, and you get an andesitic type of volcano. So here it says the same thing I just said. Partial melting occurs as some of the minerals in the rock melt, while others remain solid. Minerals with lowest melting temperatures will melt first, and silica-rich minerals have lowest melting temperatures. So when you take basaltic rock and melt it underneath a subduction zone, the silica-rich minerals melt before the non-silica-rich minerals that are higher, have high in iron and magnesium, don't melt as fast as minerals that are high in potassium and aluminum. And so they melt, and so then they start rising up because they're liquid, and then they spew out in the earth and form volcanoes. If we were in class, we'd do this experiment, but since we're not, we'll go ahead and do a picture. But let's take and put ice and wax blobs, like in a glass, in a container, and let's heat it. Okay, so when you heat the ice and wax, they're going to start to melt. And which one's lighter? Wax is lighter than water, so the wax will float on top of the water. And so when you heat it, you get wax floating on top of water, and you can see the water is about a third of the way up the cup, and the wax goes up to about halfway. And as it continues to melt, you get more wax and more water. And then when it cools, you're getting wax on top of water. In other words, it floated on top of the water. Less dense, more dense. Less dense on top of more dense. Back to the verse in Psalm 104 that I like, and you can probably quote it by now. God has created a boundary that the water cannot cross, with a more dense and less dense boundary between types of rocks. Here we see magma sources and magma composition. So you see the active volcanoes around the convergent plate boundaries. There's a few active volcanoes around divergent plate boundaries, and you can see those in Iceland and then East Africa. Well, with different plate settings, you get different types of melting of source rocks. And so basaltic magma, you'd find, like we've been talking about at the ocean ridges, where you get mantle rock that rises, and it comes up in shield type volcanoes, either on land or underwater. But where you get a divergent or spreading apart boundary is where you get a basaltic type volcano and a shield volcano. If you take and melt continental type rock, at 2 you can see a magma that's melting rock around it. You can get a rhyolitic magma. In other words, a magma that's very high in silica. And here's different types of examples. So you get a oceanic hotspot, you get a basaltic magma. You get a divergent boundary there in Iceland, a basaltic magma. And then in the Rift Valley, Kenya, Tanzania, Eastern Congo, Ethiopia, Eritrea, you get both basaltic and rhyolitic magma, because you get magma coming out of the divergent spreading boundary, but then you also get melting of the continental crust, and that creates a rhyolite. You get really interesting rocks there at that location. Then an andesitic magma, like we've talked about, when you melt the mantle rocks, you get a partial melting, and then that comes on up to the top, to the surface of the earth. Then you get an andesitic magma. So just to summarize that, you get a convergent boundary, and we got arrows pointing, yellow arrows pointing at a convergent boundary. All of those have andesitic magmas. You do get some rhyolitic magma in small quantities, just because there is some crustal melting, but the volcanoes there would be an andesite. So which image best illustrates the source of most magma from active volcanoes? Well, magma comes from isolated sources below the volcanoes. Most volcanoes are on convergent plate boundaries, and the examples you see in A and B would be divergent type boundaries. Here's a Venn diagram. Basalts would be low silica content. Both basalts and andesites would be from a mantle source, but an andesite would be originally from the mantle source, but then partially melted. The Aleutian Island volcanoes are andesitic because there's a subduction zone there. That's southwest part of Alaska, where you have Alaska stretching out into the Pacific Ocean. A rhyolitic volcano would be high silica because you're melting already differentiated continental crust. Intermediate silicate rock would be andesite. So andesites are in between basalts and rhyolites, is the way to think about it. Rhyolites are like continents, basalts are like oceans, andesites in the middle. basaltic. Hawaiian Islands are basaltic. Basalts have high melting temperatures. It takes a lot of temperature to melt a basalt. It takes a lot lower temperature to melt a rhyolite because there's more silica in it, so it melts at a lower temperature. Andesites are most common at convergent plate boundaries like subduction zones. And then all three contain silica, just in different amounts. Andesites are produced by most active volcanoes, because most active volcanoes are on convergent plate boundaries. And then all three are due to plate tectonic processes. Basaltic magma is common at divergent or spreading apart kind of plate boundaries. It's produced by decompression melting. It's where you take magma and you decrease the pressure on it. It can help melt it more than it was. Magma source for basalt magma is the mantle, and the melting occurs in andesites due to the addition of water. And in the chapter where we talked about, I think it was the last chapter, I showed a pressure temperature diagram, and it showed the addition of water, and it moved the curve. There was a diagram with an X in it, and it moved the curve over the X and created partial melting. A magma source for the oceanic lithosphere is andesitic. Well, that's because of the partial differentiation of the oceanic lithosphere that then gets partially melted when it goes down under a subduction zone. And a continental crust, when you melt continental crust, you get a rhyolite. And when you add heat to a continental crust rock, that's not said very well, but 19 assumes a continental crust, and same with 20. It's rhyolitic because it's in Yellowstone, so it's in a continent. Those last two aren't written very well, but I'm going to leave them alone. Let's see if we can identify 5 volcanoes that form above subduction zone. Right on the west coast of South America, west coast of Mexico and Central America, west coast of North America, the northeast portion of Russia, and the islands around the Philippines area, and then the islands around Indonesia. So there's a list of the plates that match each of those. And then also the Vesuvius and Etna and the volcanoes Santorini, which we think is where Atlantis was. So name a volcano that generates low viscosity magma. Well, Mauna Loa does. And Yuragon in the Rift Valley does. And Teide in the Canary Islands area does. Other than Mauna Loa, which volcano is most likely to have formed above a hot spot? Well, there's a hot spot just northwest of Africa. In this lecture, we're going to jump from volcanoes to just mountains in general. It's all in the same chapter of the book. That's a little bit unfortunate because mountains are interesting to study on their own, but there's limited space in the book, so we're going to do one lecture on mountains. First of all, it's important to remember that higher and younger mountains along convergent or boundaries that are marked in red there, where you have plates crashing into each other. And lower, older mountains represent ancient convergent boundaries. The Appalachians are an old boundary where the North American plate crashed into the African plate. then when they split apart, the Appalachians were left there, and so they're much older than the Rocky Mountains. At convergent boundaries, you have reverse faults. Remember, reverse faults are where you have faults that push together. Well, so you'd find lots of reverse faults where you get compression. And so here we have a picture of at the top of plate Indian plate coming toward the Eurasian plate, and a subduction zone under it. And then when the plates crash into each other, you have lots of reverse faults where you have faults pushing over on top of each other. If the crust is 30 kilometers thicker under the Himalayas, why are they not 30 kilometers higher than the rest of the continents? Well, there's a principle called isostasy that we need to talk about. And isostasy is an example of, let's say you get in the swimming pool, how much of you floats above the pool versus underneath the pool. Well, that's isostasy. Each person is a little bit different density. The fatter you get, the more you're going to float. The lighter your bones, you may not be fat, but if you have light bones, then you're going to float. If you have really heavy, dense bones, then you're going to sink. That's isostasy. Well, rocks are the same way. There's an exercise I like to do when I teach this in person, and that's to put water in a fish tank and put different types of wood that are different densities or even different sizes, and we'll look at isostasy, because some of that wood will be above the water and some below the water with a picture. So here we have height H, and H above the water, D below the water, and density of water is 1 gram per cubic centimeter. The density of pine wood is about half a gram per cubic centimeter, and the wood floats because it's less dense than the water. So it's about half and half because it's about half the density. So if oak was in there, most of the oak would be below the water because it's denser than pine. And so here we have an example of that with oak. Most of the oak is below the water. And notice that if the wood is thicker, there's more wood below the water than above the water, but also the wood sticks up higher. Well, the same thing's true with mountains. If you have really high mountains, then those mountains also, by isostasy, have really deep roots. They go way down into the earth. Well, how would the elevations of mountains differ if the Earth's crust were composed of denser rocks? Well, mountains would be lower because of isostasy. Here's some examples of just a comparison of how deep the Himalayas versus the central U.S. continental crust would go down into the mantle. The Himalayas are much higher than the central part of the U.S., and therefore by isostasy, the roots of those Himalayas would be much lower into the mantle than continental crust, and which is lower than oceanic crust. So one thing you want to think about is basically the reason we have land on the earth is because that verse I keep talking about, we have land on the earth because the lighter rocks float on the heavier rocks, and a principle has been put in place in the earth so that we have land. How God has used differentiation and isostasy to give us the features that we have on the earth. Well, isostasy is the balance between topography of the Earth's surface and the thickness and density of underlying rocks. The following profile shows the topography of a continent. Draw the relative position of the bases of the crust, taking into account the principles of isostasy. So if we draw that, the mountains on the right are a little bit taller than the mountains on the left, and so they would have deeper roots. Underneath that, if we label these, the lower part of the picture below the roots that we just put out there would be the mantle. Then the continental crust would be where the mountains are and in between the roots and the top of the mountains. Here's a nice picture of isostasy. It's, in a definition, it's the equilibrium of the Earth's crust, a condition in which the forces tending to elevate balance those tending to depress. Changes in elevation depend on the relative density of crust and mantle. If we pile a stack of wood up in water, and we start to remove layers, and we add layers somewhere else, one layer would have smaller roots, and the other layer would sink the roots down in. So we could pretend that this is continental crust in wood and its mantle in the water, and so the continental crust with stacking wood up on it would have roots further down into the mantle. So isostasy compensates for adding material by building a bigger root, or for lost material by raising the pile. So for every 1,000 meters of rock eroded from mountains, isostasy results in just 200 meters decrease in elevation. So here we have highlands before erosion at the top, and you have lots of erosion in the middle picture, and you don't have any isostatic readjustment, and then you have erosion with isostatic readjustment, and you can see that the land goes up a little bit. So mountains are long-lived features in the earth, and the Himalayas are still forming. They began to form 50 million years ago, and they're still forming. The lower Appalachian Mountains formed about 300 million years ago, and they're not forming anymore. They're just eroding away. And that's why the Himalayas are tall and sharp and peaked, and the Appalachians are rounded and smooth. Erosion rates on the mountains average 0.1 to 0.2 millimeters a year, depending on the type of rocks and climate and so on. So it takes 5 to 10 million years to erode about a kilometer of rock. It takes a long time to erode rock off the side of a mountain. But as that erodes, isostasy will replace 80% of the erosion. So the mountains pop back up a little bit, even though they're eroded off. So 200 meter change in elevation every 5 to 10 million years. And so it takes 25 to 50 million years to lower mountains by a kilometer, because isostasy pops the mountains back up as you erode rock off the mountain. The erosion of the Himalayan mountains occurs because you have monsoon rains that come up over the Himalayas, and they erode the mountains just because of the rainfall. And sediment from those mountains comes on down in the rivers and gets deposited in the Indus River Valley, into the Arabian Sea, and in the Ganges Delta, coming down through Bangladesh into the Bay of Bengal. Mountains influence climate patterns. Well, the monsoon rains strip carbon dioxide from the atmosphere, and that's been going on for 20 million years. So that has helped lower global temperatures by about 5 degrees centigrade, because of that removal of carbon dioxide from the atmosphere due to the monsoon rains. And the reason you get the monsoons, again, is because you get that moist air coming over India, and then it hits the really tall mountains, and when that moist air hits mountains, it goes up, it cools, and it dumps tons of rain down into northern India. So thus the monsoons.